Yes, so as I said, it's a great pleasure to welcome Professor Franz Bauer, who's coming to us from Chile. I butcher the university name, so I'm just going to say PUC Chile. That's okay. Franz originally did his PhD in the University of Virginia before moving on to postdocs. He's provided very helpfully provided an intro slide for us. Postdocs at Penn State and of course here with us in Cambridge back in the early 2000s, I believe, working with Andy before going on to take a Chandra Fellowship, very prestigious Chandra Fellowship at Columbia and joining the faculty eventually at PUC Chile. And yeah, Franz is going to tell us about fast extragalactic X-ray transients today. And yeah, so let me just hand over to you, Franz, and feel free to take it away.
Thanks very much. So as Tom mentioned, I have a very wide range of interests, and I've probably collaborated with several of you on some variety of these. But today, let's see, there we go. Today I'm going to talk about, in particular, an interest in exotic transients, fast X-ray transients. And so this is work that I sort of started, or I got wrapped up in, pulled into, I would say, is probably more appropriate. And then my student took an interest in this, Jonathan, who is in the room somewhere. And so this is sort of culminating in his PhD thesis. And so I'll give you a little bit of a history, and that'll kind of explain some of the various participants in this story. So back in the day, well, part of me being a postdoc at Penn State was I was involved in some of the early Chandra Deep Fields, and of course that carried on. And the whole big politics of Chandra Deep Field North versus Chandra Deep Field-South, and eventually we kind of picked the Chandra Deep Field-South as the field that we really wanted to go deep on. And so about five or 7 years ago, we were able to acquire a proposal that pushed the 4 megasecond Chandra Deep Field-South to 7 megaseconds. And so this was 3 megaseconds of data. And in total, the 7 megaseconds is equivalent to about 81 days. And it was published as a catalog paper by Bin Liu in 2017. And so this is just showing the field. Obviously, this is sort of the ultimate in terms of X-ray depth, and then comparing that with depth of HST coverage and essentially multi-band coverage at this point across the electromagnetic spectrum. And so we hadn't really, the way Chandra had developed, initially they would take observations, and it took many days, weeks to get the data. But by around 2014, they were they had this all under control, and actually had a nice system in place where they would observe, they would pipeline process the data as it came down, and they would offer it up almost the next day. And so although we had not really found any transients in the 4 megaseconds of the Chandra Deep Field-South, or really we found one transient, I think, in the 2 megaseconds of the Deep Field North, we decided that Bin Liu would observe the data as it came down every night, that there was a new observation, and he would go through it and see if there were any X-ray transients. And so we kind of did a next day analysis. And in doing so, we actually discovered two X-ray transients that occurred in this field. And just to put this in perspective, as I mentioned, this is a total of 7 megaseconds. Typically, Chandra observes about 20 megaseconds per year, has done so over the past roughly 21 years or so. So 7 megaseconds represents roughly 1.5 to 2% of the total data in the Chandra sort of archive. So as I mentioned, we found these two transients, and we labeled them XT1, X-ray transient 1, and X-ray transient 2. And they were relatively fast transients in both cases, with sort of total times on the order of, I guess, about 5 to 10 kiloseconds. So of order a few hours to 4 hours, something like that. And so the first one I got handed and said, okay, I'll do something with this. And this was throwing me out kind of in the deep end, because this wasn't necessarily my area of expertise. And so This is just showing an image, an X-ray image of the Chandra Deep Field-South, the 4 megasecond data. And of course, this is the position of the transient. There's nothing there. Clearly, we have other sources which are very nicely covered. And this was the observation where we detected it. It's a 47 kilosecond observation. You can clearly see this transient here. You can also see this guy, which is much fainter because it's only, it's only one exposure. And then the next observation we got was a couple days later and no object at all. And so in total, we have about 115 counts in the 0.5 to 8 keV band. This was because Chandra dithers, you can actually track its position on the chip and it moves. And so it's not an artifact necessarily, it's an extragalactic source. And it had what we call a sort of T90. So 90% of the photons came within 5 kiloseconds. These sort of effective photon index we can measure if we fit a power law to the spectrum is about 1.4 with decent constraints. And the light curve looks something like this. So the time of when it actually first went off or first started is a little bit arbitrary to within sort of maybe 10 seconds, but we see one photon come in and then a gap of about 90 seconds and then a bunch of photons comes in and then a sort of fall off. And this fall off has a sort of power law decay of minus 1.6 or so. The hardness ratio is shown here, and the hardness is just the 0.5 to 2 keV counts in the soft band and the 2 to 8 keV counts in the hard band. And so you can see maybe very, very mild spectral hardening, but not very significant. Unfortunately, so the peak flux here was about 5 times 10 to the minus 12. So it was something where clearly you can detect this in literally any Chandra observation, right? So it's very bright in 47 kiloseconds. And so if these things were common, we would detect them everywhere. In quiescence, because we have the Chandra Deep Field-South, we can actually push the limit of the quiescent flux to about 5 orders of magnitude deeper. And so it just isn't detected at all. Unfortunately, Swift-BAT was kind of looking the other direction, and the Fermi-LAT was also looking in a different direction. And so we don't have strong constraints on the X-rays above 8 keV. We have a sort of weak GPM limit, which GPM is the wider telescope from Fermi, but it's not very powerful. So effectively, it's not sampled above 10 keV. So we don't really know what the spectrum does at very high energies. And it wasn't detected by the interplanetary gamma ray network. It occurred in this really deep imaging, multi-wavelength field. And so we have HST data, very deep HST data. And it's also very well aligned astrometrically to within about 0.1 arc seconds or so. So this is the X-ray image, and this is the error circle of the X-ray image, so I think the 90% encircled energy or something like that. And this is the HST image from archival data. And this is a F606 band, so roughly a R band image. You can clearly see a nice counterpart there. It looks extended. And you can also see in the near infrared, we have some data. It's a little bit rattier, but it's detected. It's about 27th magnitude, 27.5, and it's a pretty flat spectrum across the board. It had a photometric redshift, but very, very loose constraints here. So it's 2.2, but could be as close as 0.4, could be as far as redshift 3 or so. Based on this redshift, we can estimate some of the properties. And so these are, of course, highly variable given this range, but these are kind of the rough properties. So it's a mildly star-forming galaxy, kind of LMC-like if it's at redshift 2. What was sort of interesting is that because people were observing this field all the time, it turned out that people were, there was a spectroscopic campaign to observe sources in this field that was occurring the same night on the VLT, and they did pre-imaging. And so they have a pre-image of this field in the R band 80 minutes after this transient goes off. And this is the image. It's not super deep, but this gives you a limit of about 25th magnitude or so. And so this is fairly decent constraint on the sort of prompt emission that would accompany the X-ray emission. in the optical. We also asked for DDT time, and we got force 2, deeper imaging with force 2, and so you can now see these galaxies here. Obviously, the seeing isn't quite as good from the ground, but we don't really detect anything. And then we also got a later Gemini GMOS South observation, and so we don't detect any counterpart to this event. The other event happened about 6 months later. So that was in October of 2014. In March of 2015, another source came in with an observation. This one had 136 counts. Again, not an artifact. The T90 time was a little bit larger at 11 kiloseconds. A little bit softer spectrum at a gamma of 2. Sorry, actually, this is wrong. There were spectral changes. It actually has a spectral sort of softening here over time. And it again had a fast rise. We can place constraints of about 200 seconds or so. And then it has a sort of plateau period here. And then eventually, after about 1,000 seconds, 1 kilosecond, has a pretty strong power law decline with minus 2.1. The peak flux is 7 times 10 to the 13. Again, it's not sampled very well above 10 keV. Initially, we thought this was an AGN flare. And the reason being, in the pre-event, there's an X-ray source here, which is, doesn't look like much in this image, but it's significantly detected. And this flare went off here, and because of the where it went off, which was off axis, the PSF is extended. And so it wasn't clear that these were different sources. And so initially, when we sent out an ATOW, we sent it out as this was an AGN flare. And so we didn't really follow it up so strongly because of that. And then also it happened in March of 2015, with the Chandra Deep Field-South is only up for about 1 hour at the early portion of the night. And so it's very difficult to actually get much data. It was only really observed in kind of twilight, in the first half hour after twilight, when it went off. So we didn't get any sort of optical follow-up of this event. It turns out when we actually did better careful imaging, we can decouple these two, and it turns out that this source here, this is sort of the centroid of this, is closer to this source here in the HST imaging rather than this source. And it's about 25th magnitude, 24th magnitude or so. Okay, and oops. It turns out that this offset is about half an arc second or so. And it turns out this source had a spectroscopic redshift from one of the campaigns I previously mentioned. And its redshift is about 0.74 or so. So based on this spectroscopic redshift, it had an emission line in its spectrum. We can estimate a luminosity. So again, the galaxy has a sort of modest luminosity, kind of decent sized dwarf galaxy, modest stellar mass, pretty decent star formation rate, and this kind of places it in the lower portion of the main sequence. Okay, so this is kind of what we have to work with, and the question was, what the heck are these things? And so to go through that, there's a vast parameter space of X-ray transients that have been discovered between the first X-ray flight in 1965 and today. You have variability from planets, you have magnetic reconnection events and stellar flares, you have accretion events, you have neutron-neutron star mergers, you have jets coming out, which potentially can lead to variability, all sorts of things. Given the fields we're looking at are extragalactic, given that the counterparts are very likely sort of extended sources at decent redshift, I'm not going to talk too much about these, and focusing on the things that we kind of think might be able to possibly explain them. So those include shock breakouts, tidal disruption events of compact objects around black holes, long gamma ray bursts, short gamma ray bursts, and associated kilonova. And maybe there's other things we haven't really fully thought of. So to kind of put this in perspective, this plot by DeLuca et al. Shows variability timescale versus X-ray luminosity. And this is, here this is kind of the average X-ray luminosity. So over some timescale, You have some flux, and then you have some luminosity. And these curves here are the flux just for a 10 to the minus 11 ergs per centimeter squared per second object at various distances, just to give you an idea. So our sources are a little bit fainter than this, so our sources are going to be a little bit below these lines, but for instance, at redshift 1, this sort of flux object, say if it had a variability time scale of 1,000 seconds, would have a sort of luminosity of 10 to the 44 or so. So our objects are kind of sitting in this range in here. And they go from sort of 1,000 seconds to 10,000 seconds or so. So they're kind of in here. And so, you know, they could be, again, TDEs, GRBs, shock breakouts. These all seem fairly viable. So what is a shock breakout? Initial core collapse supernovae will drive a shock through the interior. And, you know, this shock will, when it nears the surface, will become optically sort of thin, and the optical depth drops sort of as when this goes as sort of c divided by the breakout velocity, and the emission will emerge. And so depending on the structure of the star that's exploding, you know, the size of it, the density of it, you will get different sort of properties of emission that comes out from the shock breakout. These are just some formula to give various sort of the time of the breakout, the luminosity of the breakout. And so if you plug in some of these numbers, you can kind of get out rough luminosities. This is shown here in this plot. And so for compact stars, like Wolf-Rayet stars, you can see that you get a relatively short burst, pretty luminous, of 10 to the 44 or so. For much larger, sort of more diffuse or less dense outer atmospheres, you end up getting a longer duration burst, a little bit less luminous. And also note here the difference between 0.2 and 0.5. So there's a huge difference. So most of this flux is very, very soft X-rays, whereas most of this flux is relatively, well, not still a little bit soft, but not super soft. And so depending on the spectrum and the amount of time, you can kind of maybe pinpoint what type of star exploded. But the main thing is that, you know, these are pseudo black bodies peaking the soft X-rays. They have relatively fast rises, plateaus for sort of 1 or 2 dec in time, and then very, very fast, potentially very fast drops off. They typically will be in lower mass stars from the galaxies, which is kind of what we have, and they have pretty high rates. And then the post-shock breakout, you typically might see some UV emission, and then also, hopefully, a supernova that would last up to a few months later. The breast shock breakout is XRF 080109, which was detected by SWIFT, otherwise known as supernova 2008D. But there have been a few others. So that's the shock breakouts. Tidal disruption events, you have stars or any sort of compact object orbiting around a black hole. If it gets inside some critical radius, generally the tidal force will be destructive and pull it apart. And so generally half of the mass might fall back onto the black hole and circularize over sort of an orbital timescale or so. And this would then have an accretion disk, which would produce a sort of luminous flare. And Martin was sort of seminal in sort of describing these early on. So classically, the tidal radius is given by this, and the time scale over which it accretes is given by this, although these can vary depending on a variety of impact parameters and so forth. And so the thing to do is compare this tidal radius with the radius of the ISCO, the inner most stable orbit of the black hole. And you obviously need the tidal radius to occur outside of the ISCO, or else the object is eaten whole by the black hole. And so generally speaking, the tidal radius will, you know, for a bigger black hole should tend to be larger. The ISCO should tend to be larger. And so generally you will have sort of stars being disrupted by black holes can emit emission. And then if you have more compact objects, generally you need a smaller black hole to be able to still see it before it gets sort of eaten by, or falls into the ISCO. And so we might expect to see a sort of white dwarf being disrupted by an intermediate mass black hole, 10 to the 3, 10 to the 4 solar masses, with a sort of a fast rise, relatively fast rise on hour timescales, whereas the stars might be on many day timescales. And this is just sort of an example of different black hole masses and the sort of typical rise and fall timescales. And we also might potentially, because it disrupts so close, we might see it as a soft X-ray emitter. And so for Eddington limited accretion, the outer sort of disk temperature can kind of go like this, which is sort of what you end up seeing here. So you'll see more emission because it goes in further and it gets hotter. And so you end up having luminosity goes as T to the 4th, right? However, at some point, the optical range, the black body moves out of the optical range, and so you end up getting UV emission or possibly even X-ray emission. That's at least the very simplistic theory. So you should have light curves that which have a slow to fast rise depending on this, and then it should have an exponential decay, which is kind of similar to this. If you have a magnetic white dwarf, you might be able to generate a very highly magnetized disk. This could generate a corona, and so typically then you might be able to produce hard X-ray emission from that. It's theorized at least, whereas this might produce very, very soft X-ray emission. You also might be able to drive a jet, and the jet could then, of course, do beamed radiation and give you some sort of non-thermal component to that. So when you actually do the simulations of white dwarfs around intermediate black holes, actually the X-ray emission ends up being relatively stable for a pretty long time, but you can get coupling with the jet, and the jet emission can potentially produce very, very high luminosities, up to 10 to the 48 in some cases. And then you might also see a thermonuclear sort of component associated with this as it gets very, very close. You might also see afterglows and things like that. The actual observational tidal disruption events, typically you have a very wide range of phenomena. So these are two events which were beamed, Swift 2858 and Swift 1644, very, very high luminosities, which is kind of consistent with this sort of picture. But you can see pretty strong variability here. In this object, less variability in this object. They had optical counterparts as well. On the other hand, you have objects like this, which are relatively local. This is, I can't remember the XMM, well, I can see the XMM number, but it's sort of an XMM object that was found consistent with a globular cluster. And it has a very long-term X-ray light curve and very, very soft X-ray spectra, which get softer with time. And so if you consider the sort of peak X-ray emission in the soft band from 0.3 to 2 keV versus sort of its redshift, this is a nice paper by Achetel, where they compared the peak luminosities to typical accretion, X-ray accretion from AGN. And the peak luminosities from these TDEs were of order 2 orders of magnitude higher than typical X-ray emission from accreting black holes. And so most of these were relatively soft. Their hardness ratio was very, very low here. These are the two jetted ones, which I'm showing here, which had sort of a harder spectrum, as it were. But typically we can expect that these are very, very soft if they're not very strongly jetted. And they can get up to luminosities of 10 to the 44 or so. Then you have gamma ray bursts, and there's a whole history of gamma ray bursts from their sort of detection and discovery in '67 to sort of confirming that they were extragalactic in 1997 or so. Then in 1998, a year later, we've confirmed the first connection between a gamma ray burst and a bright supernova. At least for some gamma ray bursts, they seem to be from the deaths of massive stars. SWIFT was launched in 2004 and kind of revolutionized the localization of these, and therefore the study of the afterglows of gamma ray bursts. And so typically they come in two different flavors. there's this bimodal distribution of burst durations. Less than 2 seconds are short and greater than 2 seconds are long. There's a little bit of an overlap there. And it was recognized by sort of the early 2000s that long gamma ray bursts and short gamma ray bursts were separate classes. Long gamma ray bursts were thought to be related to supernova, which was based on this, whereas the short gamma ray bursts were theorized to be related to emerging neutron stars. Because they were mostly jetted emission, no two gamma ray bursts typically look alike, and so this is just a sort of view of several of them. So you can see some have sort of fast rise exponential decay, which are pretty uniform. Some have double rises, some have very sort of chaotic or complex light curves. For long gamma ray bursts, they amount to about 70% of the total gamma ray bursts that have been detected. They are generally brighter and longer, they have afterglows that are brighter and longer, and so that they end up being easier to localize. And so they're studied in much better detail than short gamma ray bursts for this region. Typically, many of them are associated with high star formation rate galaxies, and in some cases can be directly linked to core collapse supernovae. Basically, if there are huge energies, if they were isotropic, this would equal the rest mass of the sun, and so this implies that they have strong beaming, and so there are sort of models that would suggest that essentially in these core collapse supernovae, you end up having a black hole in the center, and the black hole is accreting inside this collapse, and this will lead to the formation of a relativistic jet, which will push out through the atmosphere or the interior of the star. And as it gets towards the exterior, we'll see the jet break out, and we'll see this gamma ray burst. As the jet continues out and starts to expand, you will end up seeing it over a larger fraction of the sky, and this will lead to an afterglow. And so depending on the viewing angle, you might see a gamma ray burst, or you might only see the afterglow. And depending on where, you might only see the afterglow in the radio or the optical or the X-ray and so forth. So that's the sort of general picture. Short gamma ray bursts account for 30%. Their origin was much less clear until the first afterglow was detected in 2005. Because they're so short, it's very difficult to localize them. But mostly because Swift has difficulty getting onto that location and taking an image within 2 seconds. And the afterglows don't last so long. So generally when they can be localized, they typically arise from regions with less star formation, little or no star formation, although there are some cases where they are in star-forming galaxies. And generally, they're thought to be from an older star population and associated with neutron-neutron star mergers or neutron star black hole mergers. In some cases, there are X-ray flashes associated with these, and this is thought to maybe be generated by a black hole as it disrupts debris around the remnant on a short time scale. Other observations show sort of internal plateaus, which are shown here. And these are proposed to be possibly the result of a millisecond magnetar, which is the byproduct of the neutron star. So a massive neutron star spinning very, very rapidly, and you have some sort of wind that comes off that and powers this plateau, and then maybe disappears as this the magnetar ends up collapsing into a black hole or losing energy. And so this, of course, this scenario was mostly theoretical until GW 1708-17, which was kind of a linchpin for connecting gravitational waves, short gamma ray bursts, kilinovae, and afterglows in one nice sort of package. This was not a typical event. It was a very low luminosity gamma ray burst. It's unclear how it relates to more dominant gamma ray bursts, but nonetheless, it was sort of key because it signaled that we had a neutron-neutron star merger and kind of tied together many of the theoretical results or the predictions that had been given in the 2 decades prior. So one of those predictions was from Binzhang, and so in this merger model, you sort of will merge, you'll drive a jet, and you also can drive a wind out, and this wind will lead to a kilonova. And so Bing Zhang had sort of postulated that depending on the viewing angle, you might be able to see in some range through, this would be optically thick, and you wouldn't necessarily be able to see any X-rays, but this should emit X-rays. And if you looked at the right place, over a pretty wide range of viewing angles, you might see X-ray emission. And this would be more isotropic than the gamma ray burst and be more luminous than the kilonova. And so it may be the case that a universal electromagnetic counterpart for gravitational waves might be in the primarily X-ray band. And so the overall picture of these merging sort of remnants might be you have this sort of ringing down in gravitational waves. They have the coalescence. You drive a short gamma ray burst. You might have an extended emission plateau. You might have UV emission. You might have kilonova radiation, radio transients, and you might lead to a more massive neutron star or directly to a black hole. And this would have some sort of viewing angle dependence here. And so a lot of this really depends on several unknowns about the merger process and the unknown neutron star equation of state. Of course, this all kind of would be very nice if we had a lot of neutron-neutron star mergers. However, to date, we only have one that has an electromagnetic counterpart and only two reasonable, feasible ones that seem to be reliable. And so we don't have much information about what these things look like yet. Most of what we have is black hole mergers, which is a completely other talk. Okay, so very long-winded introduction. Just to kind of give you some context. And so in the context of these various possibilities and theoretical efforts, let's now return to XT1 and XT2. Let me check my time here. Okay. So placing this in sort of this light curve in luminosity versus rest frame time, we can see this is now the bulk of gamma ray burst afterglows in the X-ray. And this is a sort of fractional plot. I also show two tidal disruption events, which were jetted. Those were the same two that I showed before. I showed two X-ray flashes here. I also show the shock breakout from 2008D. And so we don't really know the redshift very well, but the range is kind of given by this region here. And so you can see that even at the sort of top range, it's falling well below the typical afterglow from a gamma ray burst, short or long. For XT2, we show this, and so it has this plateau and then drop. And you can see it is maybe consistent with the bottom end of short gamma ray bursts, which are kind of seen here as this very, very light gray. But it's really a very low luminosity event. The other thing to sort of notice here is that typically the gamma ray bursts all have a jump up at this very, very short time. And this is because you're seeing a bleed over of the actual gamma ray emission that's bleeding down into the X-ray band. And so you get this extra component from the jetted emission as opposed to the afterglow. And so we don't see that in either of these. And so we can be pretty confident that it's probably not a weak gamma ray burst on axis because we would potentially see some of that early prompt emission in this. So other than that, now the typical thermal emission for TDEs is down here. So it clearly is not related to thermal emission. Also the spectrum is too hard for that. But it is kind of intermediate between the extremes of jetted TDEs and the thermal component. So maybe it could be coupling with a very small fraction of the overall energy budget. It's possible. We might see pretty strong variability as we see for 1644. We don't really see too much variability. It seems pretty smooth, but who knows? It is much more luminous than a shock breakout. By a couple orders of magnitude in both cases. And so we can rule out a typical shock breakout, although there may be some sort of extreme, possibly anisotropic breakout that maybe could do it. Again, the sharp breakouts are very, very soft, and these are relatively sort of harder X-ray photon, or harder photon indices. So taking kind of all of that together, and again, it's a bit hand-wavy, but just from these plots, they seem possibly consistent with jetted TDE emission from, say, intermediate TDE emission. And this has to be from a white dwarf and an intermediate mass black hole, or possibly from an off-axis short gamma ray burst. For XT1, we had the optical data, and so we can actually look at the constraints from the optical data, and these are now optical afterglows from gamma ray bursts, and so this point at 80 minutes is actually very constraining. And so this is below the vast majority of optical afterglows, and so this also actually kind of tends to suggest that even off-axis, we would have a difficult time potentially explaining it. So maybe it's a weak off-axis gamma ray burst. And then this is showing absolute magnitude, and we can also kind of exclude a supernova in the optical for a decent amount of sort of parameter space here. Again, the optical for the TDEs is here and here, and so we can kind of exclude some fraction of parameter space, but not all of parameter space. So again, an off-axis, possibly low luminosity short gamma ray burst might be reasonable. Possibly a jetted TDE might be able to explain it as well. For XT2, I mentioned this plateau and this drop, and so actually there's a model for this magnetar. So you have a merger of two neutron stars. They form a more massive, highly spinning magnetar, and over the course of about 1 hour or so, it powers this flat emission, and then it drops off when the magnetar collapses. And so you might expect a flat luminosity evolution while it's being powered, and then a very, very fast one afterwards. And so this sort of scenario was developed by a student of Benzang Sun et al. And they developed this model where you had a jet zone, a free zone, and a trap zone. And depending on where you looked, you might see this X-ray emission or not. And they modeled some light curves, and then sort of had a development of this where the light curve was fit and could give you some indication of the spin down time, or the transparent time, or the collapse time of the system in this case. And so here are a variety of different possible models, and the point being you have different components, and they might be cut off when the magnetar collapses into a black hole, and they sort of can give you different sort of components. If you have early obscuration and then it becomes optically thin, you might have a turn on and then a sort of peak, and then if it collapses, you might lose it again. So in this context, Sun et al. Was able to explain both XT1 and XT2. And so XT2 was sort of from a viewing angle that looked like this. So it was not being totally absorbed by the ejecta. You could see it early on. And so you could see the magnetar powering and then the drop. And then XT1, sorry, was initially obscured by the ejecta. And so it's obscured here. And then at some point becomes optically thin and you see it. They also were able to explain gamma ray burst 170817 as being something similar to XT2, which is sort of intriguing. Now, this is one model, not necessarily the correct interpretation, but at least it fits most of the pieces. So a big question we had was, why the hell did we detect 2 of these in 7 megaseconds? And no one has really detected many of these in the Chandra and XM archives. Just a simple extrapolation would suggest that we should see hundreds of these in the archives. And so is it just that people didn't notice them? Or did we just get really lucky in the Chandra Deep Fields? And so this was a question that kind of nagged at us. And so a student of Neil Brandt, Guangyang, did a search through several different Chandra surveys, which had nice uniform coverage. And so about 19 megaseconds, and so roughly doubling or so the grasp of our survey, no new detections. He basically detected XT1 and XT2, and that's it. And this is his sort of results. And he's pushed the rates down a little bit, so implying that maybe we expect many tens of sources in the archive, but still that's tens of sources. Where the hell are they? And so can we find further X-ray transients? And this is the goal of my student, Jonathan Carolla's work, is basically to identify objects that might look like these things. We're only presenting Chandra here, trying to, Chandra has the best localization, and therefore we can try and find the hosts better than, say, XMM. And so we're only presenting Chandra here, but we are also looking at the XMM archives as well. And the key here is to try and characterize concurrent emission whenever possible. This is very rare. You have to get very serendipitously lucky, but also to study their host galaxy properties and use sort of all the information available to us to obtain redshifts, characterize the host, stellar mass, star formation rate, metallicity, etc. And eventually we would like to compare them with other events, other gamma ray events if they actually end up being detected, short gamma ray burst hosts, afterglows, etc., past TDEs, etc. So the methodology, we actually use two different, we end up using as a preliminary feeder catalog, the Chandra Source Catalog DR2. And we use only the observations greater than 8 kiloseconds, mostly because after that, we can't tell that something is very transient or not. And so this amounts to about 170 megaseconds or so. And so this is almost a factor of 20 over the Chandra Deep Field-South study and a factor of about 9 over the Guangyang study. And this, the DR2 goes out to 2014. And so we made a cut above a certain galactic latitude to remove stellar contamination, which is very, very bad. And so we end up studying about 200,000 sources or so. We look at the light curve and we try and match to a fast rise exponential decay, which fits both XT1 and XT2 very well. But we also use a less conservative method, which is an excess variance method developed by Guangyang. And essentially what that does is just takes two halves of the data, compares them, and if there's an excess in one half, it's a candidate. And then we go through and look in more detail at what it is. And so this is much less conservative and finds a lot of things which have very interesting variability, but not necessarily XT1 or XT2 like variability. And so these are the results. Shown here are the total candidates. And then finally, after we find the candidates, we go through the archive and we look for sources which were detected multiple times. And so we have something like 400 possible candidates between the two methods. And of those, roughly about 300 have second or third or fourth observations. And about 230 of those end up being rejected or detected in those other observations. We also cross-match with Gaia and with deeper catalogs for stars, and we reject a significant amount of sources based on their counterpart. They have bright, R of 20 or brighter sources that are consistent with the position of X-rays. And so you can see we've rejected most of the candidates by now, and so we only have about 40, 50 candidates now. We go through NED, all the catalogs, all of the archival imaging to further reject sources. We then look at instrumental effects, and the final vetted sample is about 14 objects, 14 detected by the Yang method, and then 4 of these are concurrently detected by the Fred method. I just show the sky position of those in the red stars. There are 2 sources which are known, XT2 and XRT 170838, which happened after 2014. And so those we include, but they're not part of the complete sample. Whereas XT1 happened in 2014 and is actually detected. And we confirm that these 3 transients would have been detected by this methodology. And so this should deliver XT1 and XT2 like candidates. In terms of the counterparts, it's a huge range, and actually what we didn't really expect was for 6 of them, they're actually consistent with local local galaxies inside of about 30 megaparsecs or so. So you have, for instance, counterpart with SEN-A, M86, M08. Of these 6, 4 of them end up being consistent with star-forming regions. And so very likely they're associated with some sort of high mass X-ray binary or some sort of young magnetar, anomalous pulsar, that sort of type of source. In two cases, this is possibly a globular cluster in Cen A, and this might be associated with an older stellar population, maybe a neutron or black hole binary that just had a flare. This one is unclear. We don't have terribly deep images, so we can't really put a constraint on it. For the rest, they generally are distant. This one doesn't have a counterpart. A few of them have counterparts, and we have potential redshifts for a few of them from follow-up spectroscopy. So you can see here, here, and here, we have counterparts. For this one, we don't. For this one, we don't. For this one, we don't. We can place limits on them. I don't show XT1 here because it's included in the sample, but I already showed it. We also include XT2, and we include 170831, which has a GRISM HST redshift, a single line, which is either redshift 0.6 or 1.9. We look at the hosts for the ones where we can reasonably identify hosts. And for the most part, they're here, 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 here. They seem to be on the main sequence. This is just the main sequence for redshift 0 shown. And so the main sequence evolves. And so at redshift of 1, it should sit around here. So they're kind of consistent with main sequence galaxies, but there are large, decent sized error bars because the photometry is not super great. So given we kind of have some luminosities or luminosity constraints, we're assuming for the ones we don't detect that they're extragalactic, relatively faint hosts at high redshift. So we assume the redshifts are greater than 0.5 based on our decam imaging. And so that places them somewhere here. And so going back to that original plot I showed, we have peak luminosities of sort of 10 to the 44 up to 10 to the 47. And time scales between 1,000 and 10,000 seconds typically. And then the galactic, or sorry, the nearby extragalactic sources are sitting down here, and they typically have luminosities, peak luminosities of 10 to the 38 to 10 to the 42 or so. So there are some sort of somewhat known phenomena. In general, the light curves here, they have multiple constraints, but the detection is typically the best constraint. And so many of the constraints are at higher fluxes, and so they may be detected multiple times. And so we may have more examples of these in the sources we rejected. Whereas these sources tend to have consistent fluxes and would have been detected multiple times. This is what the nearby sources look like in terms of their light curves, a bit of heterogeneous sort of mix of sources, but you can see they're very, very kind of low luminosity, typical of relatively nearby sources. And then these are the more distant sample, and we show a range of redshifts here. And so this you can compare to the plots I showed before for XT1 and XT2, and they fall in pretty similar regions of parameter space, although in some cases the light curves are more complex. And I'll show that a little bit in the next slide. Here's XT1, here's XT2, and here's XRT 170831. So we fit this with the light curve with either a power law or a broken power law, or we classify it as complex. And so for the nearby sources, you can see again that they show a pretty wide range of light curve type, with several of them being complex. And then for the distant ones, about half of them, or 6 of them, show some consistency with a broken power law. So XT2-like, and several of them are very flat. This is XT1, which shows this sort of absorption. And then a few of them are more complex. And then this one's just a power law, but these 3 are complex. And so in theory, we can fit these with this proto-magnetar model and pull out spins and magnetic fields and kind of understand some of the constraints, but there also is a degeneracy with the redshift. And as it turns out, the redshifts we have and the host galaxies we have are for this object, and this object. And so we don't actually have redshifts for these. And so there's for 3 of them. And so there's a problem. In terms of spectral slopes, this is the range. And so these are XT1 and XT2. You can see most of the other sources. This goes from very, very soft to very, very hard in terms of hardness ratio. Many of them are relatively soft, but 5 of them are decently hard, including XT1 and XT2. We can compare this with the range for short gamma ray bursts. And so in terms of hardness ratio, or sorry, photon index, they would sit kind of here. Hardness ratio, they would sit up here. And for the sources where we have significant, 100 counts or so, we can measure the spectrum. And so that's why this is not the full sample. You can see many of them tend to have softer effective photon indices than short gamma ray bursts. We also try to fit with various models. The power law model generally is a better fit than a black body or a bremsstrahlung. So conclusions. We see a very, very mixed origin for these extragalactic transients. For one, there's nearby versus distant, which have completely separated luminosity classes. In terms of the nearby, 4 of them are associated with star-forming regions. And so we can kind of associate them with relatively young phenomena. So either high-mass X-ray binaries, magnetars, anomalous pulsar phenomena, etc. 2 of them might be from an older sort of classes system. Then for the distant ones, about half of them, a little more than half, show these broken power law light curves, have power law spectra between 1.5 and 3. We have 3 faint hosts, and the limits on the other hosts are consistent with the magnitudes of the 3 faint hosts. And we think probably these are reasonable counterparts for a neutron-neutron star merger to a magnetar, kind of consistent with the Zhang and Sun sort of predictions. 3 of them show complex light curves that are not very consistent necessarily. Maybe these are still off-axis gamma ray bursts. Maybe they're tidal disruption events that are jetted, not clear. And then 1 source, which is a power law, which again could be these things. So those are our conclusions. They're not very tight or strong. Unfortunately, in terms of event rates, the total event rates are kind of consistent with what we would predict if we extrapolated neutron-neutron star mergers out without much evolution. And if we expected some evolution, we'll probably still be kind of okay. Only a fraction of these are maybe mergers, so this might go down by a factor of 2. We can consider this, we can compare this to the expectations of unbeamed long gamma ray bursts or short gamma ray bursts or low luminosity gamma ray bursts, and they're a little bit higher, but perhaps within the uncertainties. And so, there are a decent number of them. We've put pretty different constraints on them, but there is now a question. One, we want to characterize the counterparts a bit better. We want to detect the fainter hosts and confirm if they're 25th, 27th magnitude, what their star formation rates are, what their redshifts are, lock down the luminosities. We're also thinking about searching for counterparts in XMM and Swift. The puzzling thing is that, okay, we detect of order 10 extragalactic distant sources. Extras was a project to look for transients in XMM archive, and they largely came up with none. And we're sort of scratching our heads about why. Maybe it's that these things are rejected in the reduction somehow. Maybe they're hard to find. Maybe there's some issue that we haven't thought of yet, but it's sort of puzzling. And so when we apply our exact search methods to the archive, hopefully we'll have a better answer to this. We obviously want to study the 6 transients in better detail. Possibly throwing some more complex models at them, but there are huge degeneracies here, so it's not clear how reliable those things will be. And obviously we want to consider other possibilities, so we need better models of jetted TDEs, possibly exotic shock breakouts to throw at these things. In the near term, E-Rosita is observing. E-Rosita technically has a grasp of 6 times that of XMM, below 2 keV. And so at least for the softer versions of our events, we should start to see them in E-Rosita. The problem is that the grasp at harder X-rays is actually worse than XMM. And we also don't detect them in XMM for some puzzling reason. So it's not clear what E-Rosita is going to deliver. The other problem is that the way E-Rosita scans, it only is on a particular source for about 250 seconds. And then it waits, it has to go around, and then it'll get it again 4 hours later. 4 hours is about 14 kiloseconds, and so the best we can really hope for is on and then off, and that will be our transient. And so hopefully eROSITA might be able to turn around and identify some of these things. But I don't have my hopes too high for that. Longer term prospects, there are many X-ray missions such as Athena, Einstein probe, Thesis that are kind of predicted to be launched in the 2030s-ish era. They have much better grasps and potentially could accrue a larger number of these objects and actually give us statistics. The benefit is that by that time, most of the sky will be imaged to 27th magnitude. And so the host will be relatively well characterized, as well as we can probably do. Real-time follow-up may still be problematic. And then the other interesting option is gamma, these gravitational wave observatories and the multi-messenger follow-up. And so potentially by 2025, 2026, we might be able to slew telescopes over and be able to detect faint X-ray signals from these. And that might be a nice tie-in to connecting the more distant X-ray transits that we're finding in Chandra with the more local events. Okay, so I'm done. I will stop now. Went a little bit long, but thanks for listening to me. And please, let's hear questions.
Thanks, Franz. Yeah, you can't hear the applause going on around everybody's living rooms, bedrooms, kitchens, whatever, but it's happening. At this point, let me stop the recording, and yeah, we can move on to a few questions, I think.